Wait for a few minutes to check if anybody will join this meeting. Hello, Rajit, am I audible?
Yes, sir. Audible, sir.
Okay. Okay, we'll wait for a few minutes. We'll check if more people will join this meeting.
Okay, sir.
So, in the last few lectures, uh, the class was on the statistics, right? The statistical mechanics, Maxwell-Boltzmann distribution, Fermi-Dirac distribution, right? Hello.
Yes, sir.
Okay.
It was on statistics.
Okay, sure. So we will have questions in which we will solve some problems on the statistics only. Just
Actually,
give me
now.
one. Can you repeat? Okay. Karthik is here.
Good afternoon, sir.
Good afternoon. We'll start in a couple of minutes.
Okay.
So, are you all enjoying this course? Hoping the answer is yes. Okay, let's start. Uh, am I audible? Hopefully, I'm audible.
Yes, sir.
Okay, so in this class, we'll discuss about the Fermi-Dirac and the uh, Maxwell-Boltzmann statistics, and like how they are important for our materials, for understanding the physics of these materials. So we'll start with the first question. So it's about microstates and macrostates. So the first question is, number of microstates are also dash like number of macrostates for a system at a constant energy, pressure and volume. So are the number of macrostates fixed? Can they increase? Will they decrease? Or is it like undefined? We cannot say what will happen to these macrostates. What do you think the answer is?
Fixed.
Fixed. Okay. guessing there's nobody else here. Yeah, Rajit is here. Okay, so so let us discuss about microstates and macrostates. So one of the easy ways that I think we can understand this, if we take the example of, let's say, a balloon. So a balloon, if you look at it, it has a certain pressure. There's a temperature, the atmospheric temperature, ambient temperature, and a fixed volume. Now, these are the macroscopic properties: the pressure, temperature, and volume. But if you look at the atomic scale, you will see that the origin of this pressure is because of this gas particles. These gas particles are everywhere, and they hit the wall. When they hit the wall, there is an outward pressure, and then there is a balancing pressure, which is like in the form of a tension in the balloon or some other way, which balances this pressure. So we can, so the all the macroscopic properties are the macroscopic properties. They are like the pressure, the temperature, the volume. They're determined by the microscopic properties of the gas molecules. So each of these gas molecules have a specific kinetic energy. It has a specific position, momentum, and all those things. So for all the like 10 times n particles, where like n is like much greater than 1, you can define a specific kinetic energy position for all of these particles, and they together they they have a macroscopic behavior, which results in a property like the pressure, the temperature, and the volume. So this is the difference between the macroscopic and a microscopic property. Now, what happens to this microstates when at a specific macro state? So we can take the example of, let's say, two dices. So if we have two dices, and if we check all the probable combinations that we can get from them, so you can have two ones from them, you can have a 1 and a 2, you can have a 2 and a 2, you can have up to, you can have 12, like 6 plus 6. Now if you see, this is the probability, this is the probability, size the probability, sorry, probability, and this is the sum. So the probability of the sum being 2, the probability of the sum being 3, 4, all this. So you can see that total 36 microstates possible. So with the with for the macrostate of 2, we have only one microstate. For a macrostate of 3, we have two microstates, and for the macrostate of 7, we have the highest number of 6 microstates. So even though the probability of the microstates are different, the total number of microstates are fixed for a fixed number of macrostates. So the answer is right. So the if at a constant energy, pressure, and a volume, so at a constant energy, pressure, and a volume, we will have a fixed number of microstates for a specific macrostate. So in this case, okay, we'll look at into the next question. So I hope you understood this question. The answer was correct. So we'll move on to the next question. The next question is, microstates are dash, and probability of dash probable state increases with increase with the number of particles in the system. Not equally probable, none of the, equally probable, and less. Not equal. Sorry. Not equally probable, more. Equally probable, more. What do you think is the answer?
C.
Microstates are not equally probable, and probability of more probable state increase with the number of particles in the system. Okay, Rajit says B. So there are two answers here. Okay, so we'll look at this question with an example. So first of all, we see that in this case, we see that all the microstates are not equally probable. But this is fixed. Like the number of microstates are fixed here, and it's a two die system. But let's check. Let's change the number of particles. Just basically, we're changing the macro state. The number of particles is also a macro state. We're changing the macro state of the system, and we'll see what happens to the probability of the micro states. So this example also would have encountered in the classroom. So let's say we have a macro state with total energy 3E, which where E is the energy and n number of particles. So if you see here, if there are only two particles and if you want the total energy to be 3E, you can either have one particle with zero energy and one particle with energy 3E, or one particle with energy 2E and one with 1E. So the probability of finding each of them is equal. So there's a 1:1 probability of finding of not finding of each of these microstates to exist. If you increase the number of particles by 1, in that case we have three possible microstates. You can have two electrons with zero energy, two particles with zero energy, and one with energy 3E. You can have one particle with energy 0E, one with 1E, and one with 2E, and one particle with energy 0E, three particles with energy 1E, and none with 2E and 3E. You see that in this case, the probability of finding these microstates change from 1:1 to 2:3:1. Sorry. So if you just check like the two most probable things, like this one and this one, it changes from 1:1 to 1:2. And similarly, if you increase by one more particle, you see that these are the corresponding probabilities. And if you check the two nearby probabilities of occurrence, it increases from 1:2 to 1:3. So you can see that the most probable microstate, the probability of finding the most probable microstate also increases as you increase the number of particles. So the answer is in this case C. So all the microstates are not equally probable. We see here that it's 1:1, 1:2, 1:3. We also see here that the microstates are not equally probable. It ranges from there can be 6 of one to only 1 of one, and they increase. Their probability increases with the number of particles in the system. So the answer is C. B is not the correct answer. Rajit, is this okay? Like you had given option B, so is this answer clear to you? Okay, this is probably not in this class. Okay, we'll move on to the next question. So the next question is, one of the justifying reasons behind the failure of the Drude model for specific capacity is volume, pressure, particle numbers, energy distribution. Any answers? Any guesses?
Between C and D, confusion.
Okay, between C and D there is confusion.
Feel it's D.
D. So you think? Oh, sorry, you're not audible properly. Okay, Tamagna says D.
I have a confusion between C and D. That's what.
Okay, I have a confusion between C and D. is an internet issue from my side. Okay, we'll discuss this question. So first of all, we'll define what is this specific heat capacity. So this is the quantity of heat absorbed per unit mass of material when its temperature is increased by 1 Kelvin. And the unit is its heat absorbed, joules per unit mass, so it's kg per Kelvin. Joules per kilogram per Kelvin is the unit of specific heat. So basically, this talks about how much energy we need, how much energy do we need to supply to the material to increase its temperature. That is a specific heat. If something has a very high specific heat, you have to apply a lot of energy to increase its temperature. Okay. Now, so and this can be explained by the two statistical distributions which we had discussed in the last week's lectures. So one of them is the Maxwell Boltzmann distribution, and second is the Fermi Dirac distribution. So I will just call it MD from here onwards, and this is like Fermi Dirac is FD. So if I would have looked at this MB distribution, the Maxwell-Boltzmann distribution, so in this case, the probability of finding a particle at a certain energy level is given by, let's say, F Maxwell-Boltzmann at energy EI is proportional to exponential of minus energy EI, energy level EI by kBT, where kb is uh, the kb is a constant and T is the temperature. And another condition is that this summation because if we take all the energy levels from 0 to infinity, all the particles must have been covered, and so the probability should be 1 of finding any particle in this range. If we plot this, we have something like, so let's say we draw the distribution of these particles, let it be n. So even like n is, even this is like, we can also write this as in the following way. Like number of particles in energy I, number of particles at energy level EI is equal to n naught, which is the total number of particles. Let it be proportional. Total number of particles to exponential minus EI kBT. So now if we plot this quantity, the number of particles at energy location, energy level EI with the energy in the x-axis, we have a distribution like this. So what this means is that we have several particles here, and their concentration decreases, their number decreases with an increasing energy. So when you apply heat to the system, this particle can like take more heat and move to this energy level. This can move to this energy level. This can move to this energy level. So electrons in all the energy levels can absorb heat. Electrons in all energy levels can absorb heat. And now, since all of them absorb heat, the amount of heat required to increase the temperature also increases because all the electrons can participate in the process. But what happens in the Fermi-Dirac distribution? So here, the probability of occupation, let it be FD, where F is the probability and FT refers to the Fermi-Dirac distribution. So at probability of occupation at energy level EI is given by 1 by 1 plus exponential the energy level EI minus the Fermi energy by kBT. The kB is the Boltzmann constant and T is at the temperature. Now, if you plot this, what we see, so if you have probability on the y-axis, it's 1 here. So at a certain temperature or a certain energy, so if T is equal to 0, we have a distribution like this. And as you increase the temperature, you shift to some profile like this. So now what happens? So in the case of the Maxwell-Boltzmann distribution, all of these electrons would have absorbed heat. All of this could have absorbed heat. But in the case of the Fermi-Dirac distribution, if you see here, let's say this particle here absorbs the heat and it wants to move here. But all the states are already occupied here. So this is not allowed. This is cancelled. And so electrons in this regime, so the electrons in this regime, they cannot absorb any heat. But electrons here, but electrons at this location can again absorb heat and move to at higher energy location. Electrons can from here can absorb heat and move to higher energy location. From here they can move to higher energy location. And so what this means is that in the case of Maxwell-Boltzmann distribution, all electrons can absorb heat. Whereas in the case of Fermi-Dirac distribution, only electrons with energy around the Fermi energy can absorb heat. So what this means now? So what this means is that you have to only heat up a smaller number of electrons to increase the temperature of the system, and therefore the energy distribution is responsible. The energy distribution is responsible for explaining the difference in the specific heat that is observed. So we had earlier seen that we are overestimating the CV. So we are overestimating CV by 100 times. That is because we're considering the Maxwell-Boltzmann distribution. We're considering more number of particles. We're saying that all the electrons are participating, whereas actually only a fraction of them are participating by the Fermi-Dirac distribution, which corrects this. So the energy distribution is responsible for explaining the failure of the brood model. So, did you get the answer, Karthik? Is the answer clear?
Yes, sir. Yes.
Okay. You can ask me if you have any doubts. Okay. Okay. So we'll move on to the next question. So physicists choose a constant temperature and volume system to understand the model and experimental results because energy levels are identifiable, energy levels are fixed for a constant energy of the system, energy levels are not identifiable, energy levels are not fixed for a constant energy of the system. Tamagna says B.
Both A and B.
Okay. So you are seeing both A and B. Okay, Tamagna. So if you would have looked at the let's say the energy levels in the case of hydrogen atom, you will see that the energy levels are well defined. We know how much energy is required to remove an electron from a hydrogen atom from here to the vacuum level. So you need 13.6 eV of energy to remove this electron, and so the energy levels are identifiable. So, so this is a wrong assumption. The energy levels are indeed identifiable, and the energy levels are also fixed for a constant energy system. So both of you were correct. So in the upcoming class, we will also learn about how, like why we are saying this. We will derive this expression to find out the number of energy levels in the system with a fixed volume. So we'll move to the next question. We'll move to the next question. Free electrons in the Drude model of a univariant solid are presumed to have dash behavior and that they follow dash. We had discussed this question in the as the last question in the previous class.
C.
Yes, you're right. Tamagna, I hope the answer is clear. So in the Drude model, we had assumed that we are applying the kinetic theory of gases to. So I will write it here. So we applied kinetic theory of gases, which basically follows the Maxwell Boltzmann distribution, and which is why we had overestimated the specific heat by 100 times. And when we applied the Fermi-Dirac distribution, we see that we are correcting for the number of electrons that are encountered in the process, and so we are correcting for this value of CV. Okay, so next question. While deriving the expression for the Maxwell-Boltzmann distribution, it is assumed that change in the total energy of the system is zero, change in the total number of particles in the system is zero, change in the product of total number of particles and system energy is 1, change in the total energy of the system is a non-zero constant. What do you all think is the answer? Any answers?
So yeah, total energy of the system is zero.
System is zero. Tamagna?
So we are telling they're distinguishable, identical and distinguishable. So number of
Uh,
particles also can tell A and B.
A and B.
Yeah.
Okay, so you are correct. The answers, the answer are both A and B options. So we say that the delta E is zero. So the net energy change, that there's no net energy change, and also we are saying that the number of particles of system is the total change in the number of particles change is zero. I mean, the number of particles is not zero. Change is zero. It's non is zero. So we have taken a macro state in which we have fixed the energy and we have fixed the number of particles, and then we have an expression for the Maxwell-Boltzmann distribution. So answer is both A and B. So you were correct. I hope there is no doubts in this question. I don't see any questions in the chat box. Okay. Yes, Tabagna, B as well. Okay. So we discuss the next question. So the most probable microstates of a system gives information about the dash, number of particles that have escaped the system, changes in the positions of the allowed energy states, number of particles at each energy level, and the equilibrium state of the system.
C and D, sir.
C and D. Any more answers? So if we look at this example, so when we have a specific microstate, we know like which electrons are in which energy level. So we do know like which electron is in which energy level. So that is the option C, number of particles at the energy level. And the equilibrium state of the system is defined by the most probable microstate. Like when you have a large number of uh, microstates possible, one of them will completely dominate over the others, and most probably will be always be observing that single microstate because of its very high probability, and that becomes the equilibrium state of the system. So both options C and D are correct. I hope it's clear.
Yes, sir.
Okay. So next is a true or false question. Particles are identical but not distinguishable. So like identical but not distinguishable are not the correct assumption of Maxwell-Boltzmann statistics.
True. Those particles are identical and distinguishable.
So the particles are identical and, distinguishable. So I will. So in the Maxwell-Boltzmann statistics, in Maxwell-Boltzmann statistics, we apply the classical mechanics with the theories of classical mechanics. So what do I mean by the theories of classical mechanics? Is that there's a level of certainty. There's a level of certainty. So we know, so we can track, we know the position of each particle, and we also know the location and the momentum, and like for example, which direction they are moving. So what they mean is that, let's say I have two like spheres which look identical, so they may collide, and then they will bounce back to different directions. So even though they are identical, we know that which particle moved in which direction. So even though they are identical, we can distinguish that, okay, this particle is different from this particle. This is what we mean by the particles being identical but distinguishable. Whereas in the case of electrons are actually fermions. The word fermions come from the Fermi-Dirac distribution. So which follows the principles of quantum mechanics. So we will be talking about quantum mechanics in the upcoming classes. We will be solving some questions of the quantum mechanics also. So in quantum mechanics, we have uncertainty. So you would have heard about the Heisenberg uncertainty principle. So we do not know so this is a probability. We do not know the exact position of the particles is not known. We only know that where is the probability. We only know where the probability of finding the particle is high. So because of this probability, because of this probability, we cannot exactly distinguish when two particles come, that which particle is in which position, and so it's difficult to distinguish. Which is why in Fermi-Dirac statistics, the particles are identical and indistinguishable. So this is the particles which follow this are called fermions. An electron is a type of a fermion. Electron, so it's one of the example is electron. So electrons are fermions, which are basically identical indistinguishable particles, which follow the principles of quantum mechanics, and we have to apply Fermi-Dirac statistics to electrons and fermions. So yes, so in Maxwell-Boltzmann distribution, the particles are distinguishable. Maxwell-Boltzmann statistics, the particles are distinguishable, and so the answer is true in this case. We'll move to the next question then. When the temperature of a system is lowered from 500 Kelvin to 300 Kelvin, the particle population will dash at dash energy levels, a dash energy at dash energy levels is predicted by the Maxwell-Boltzmann statistics. So another way to like ask this question is that if I have uh, two distributions like this, so we have a Maxwell-Boltzmann distribution here, and we have a distribution here. So, which one has a higher temperature, T1 or T2? Any answers? So this is Maxwell-Boltzmann distribution. Any answers?
Sir, with the decrease in temperature, the particles at the higher energy level will return back to the lower energy.
With decrease in temperature, the particles at the high energy level will come back to the low energy level. Yes, right. You're right.
So it increases at the lower energy level and it decreases at the higher energy.
Yes. Basically, A and D. Yes, right. You're right. And can you tell in this plot which one is at a higher temperature, T1 or T2?
T T1.
T1 is at the higher temperature. So if you are increasing, so what you said, if you are that if the temperature is increased, probability of finding or the number of particles with higher energy will also increase.
Increases.
Right. So
Yes.
so some at higher energy level will also increase. So in this case, if you compare these two, so at this energy level, we see that T2 at this is for T2. So concentration here is higher compared to the concentration here,
Yes.
and at lower temperatures and at lower concentrations, you can see that it's lower here compared to here. So T2 is actually at a higher temperature than T1.
Okay.
Is it clear?
Yes, sir. Yes.
At higher temperatures, the particle population will be higher at higher energy levels, and particle population will be lower at lower energy levels. Basically, option A and D.
Yes.
So these regimes can be written as exponential minus E by kT. It exponentially falls down in this region. It's okay, right? We'll move to the next question. The particle position is dash for the classical particles when compared to the quantum particles. We discussed this a few minutes ago.
A1 clearly identified.
Yes, you are right. So particle position is clearly identifiable for the classical particles when compared to the quantum particles. Yes. So classical particles are like gas molecules in a balloon, which was the example in our first question. Then quantum particles are like electrons in a metal. So we have this de Broglie wavelength and everything, right? So as the mass of a particle decreases, it becomes more and more wave-like, and so it's difficult to pinpoint the actual exact position or the momentum of the particle by the Heisenberg's uncertainty principle. We'll be discussing about all this in the next class. Okay, so now we'll discuss a little bit more about the Fermi-Dirac distribution. So at the Fermi energy for a metal at temperature equal to 0 Kelvin, what is the probability of occupation?
Half.
Of any particle. So we have this distribution, right? So let's say we have this probability of occupation of a particle at a certain energy level, any fermion of any, for example, let it be electron. And so at temperature T is equal to 0, we have like this, and we call this the Fermi energy, which I'll say EF, and this is the x-axis is the energy. So this is the profile at temperature equal to 0 Kelvin. So what is the probability of occupation at this energy?
Yes, sir. Half.
So at T is equal to 0, there's a sharp drop from 1 to 0 at the single energy level. What it means that if you would have, let's say, drawn these energy levels, at energy level is increasing. So at a particular energy level, all the like particles are occupied, and just above that there is no like particle, and so there's a sharp drop from 0 to 1 just above this energy level, and therefore the probability of occupation is undefined at this energy level because there's a sharp drop from 1 to 0.
Okay, sir.
Now, what your answer was correct if it was at a higher temperature. Now, what will happen if we increase the temperature? Okay, so this is 1. I'll draw it again here. This is the probability, the Fermi-Dirac distribution. The probability of 1, this is probability of 0. So this is at T equal to 0, and this is at some higher temperature, T greater than 0. So in this question we ask that for a system at room temperature, following Fermi-Dirac statistics, the probability of occupancy of a state at an energy level marginally less than Fermi energy is nearly 1, slightly higher than 1, half, slightly lower than half, or is it nearly 0? What do you think is the answer in this case? So where it intersects, it is half. So if we are marginally like at a energy level slightly lower than EF, we are somewhere here. The probability of occupation in this point is greater than half, slightly higher than half. The answer is B. So you can also write down the equation for this, where F Fermi Dirac is given by 1 by 1 plus exponential EI minus this is at a EF by PD. So if you are at a energy level slightly lower than EF, we say this is greater than half, but it's greater than half, but it is smaller than 1. So the answer is B. Is it clear? Your answer was correct in the previous case. It would have been half only when temperature is at a greater than 0 Kelvin. Did you understand? Is it clear?
Yes, sir.
Okay, so we'll move to the next question. So at room temperature, in the process of exchange of energy with the surroundings, the fermions that participate in the process are fermions close to the Fermi energy, all the fermions, only fermions above the Fermi energy, only fermions below the Fermi energy. So you remember we discussed this question, right, on the specific heat. So we discussed in this question that since probability of occupation is like uh, 1 here, there's no electrons cannot take in, or they cannot move at their location. Like they can't lose their energy or they cannot gain energy. Both of these are not allowed. Both losing of energy is not, gaining energy is not allowed. So if you again draw this here, so let us first define EF. This is 0, this is 1. So electrons in this regime, they can both neither with just this region cannot gain or lose energy because the probability is 1. Probability cannot increase beyond 1. Only the particles, only the particles near this Fermi energy, they can participate in the energy losing or gaining processes. So the answer to this question is fermions close to the Fermi energy. So both fermions below, so both above and below and at the Fermi energy, all these electrons can take part in the energy exchange processes because there are states available. So if it is half, the electrons can either gain energy and move here, or they can lose energy and move to the lower energy levels. Both gaining and losing are allowed in all the particles near the Fermi level, near the Fermi energy. Is it clear?
Yes, sir.
Okay. So I'm not going much into maths. Like we can also solve these questions by putting in numbers, but I was just trying to explain it. My figures. So finally, this is an additional question. So do you think do you think if there is any relationship between the Fermi-Dirac distribution and the Maxwell-Boltzmann distribution? So if we write the Fermi-Dirac distribution again, So you will see that if this value is much greater than 1, which is possible when EI is much larger than the Fermi energy, it isn't to be much greater. It depends on the temperature. So if EI by kBT is this is like much like greater than the EF by kBT, then this is equal to exponential of negative EI minus EF by kBT. Now this is exactly similar to the Maxwell-Boltzmann statistics. So the Fermi-Dirac statistics converge to the Maxwell-Boltzmann statistics when this value is much greater than 1. So it's not like they are two completely different entities. So Fermi-Dirac can also, the fermions can also act as classical particles because these are quantum particles applicable to fermions, which are like quantum particles. And Maxwell-Boltzmann is for classical particles. So even electrons, which is a quantum particle, can behave as a classical particle with the Maxwell-Boltzmann distribution at energies at energies in which satisfies this condition. Uh, then the particles act as classical particles, and we can directly apply the theories of Maxwell-Boltzmann distribution, the ideal gas theories. Is it? Did you understand this part? Hello, is anybody there?
Once again,
Okay. So this is the from Fermi-Dirac distribution, right?
yes,
So if let's say if this value is much greater than 1, then you can write it as almost equal to 1 by exponential EI minus EF by kBT, right?
yes,
This is basically exponential minus exponential minus EI minus EF by kBT, right?
yes,
And we have seen from Maxwell-Boltzmann distribution that Maxwell-Boltzmann, that probability of occupation of energy level EI is proportional to exponential minus EI by kBT, right? This is basically this. So this is nothing but K into exponential minus EI by kBT, right? Where A has the EF term and it is a constant at a temperature. So these two converge at conditions in which this value is much greater than 1.
okay,
Is it clear?
yes, yes,
So what this means is that this is applicable for classical particles, and this is applicable for fermions,
quantum,
which are quantum particles. So the quantum particles can also behave as classical particles at under certain conditions, and this is that condition. So even though the distributions are different, under certain conditions, they both can act as classical particles. So this is what I wanted to discuss in this question. Is it clear?
Yes. Yes. Yes.
Okay. So it is 4 p.m. and I don't have any more questions. So I think we can stop here. I hope you got some insight into some of these concepts.
Yes.
So
Clear.
okay. So thank you for joining. If you have any questions or I think we can stop the class here.
Okay. Thank you.
Welcome, Tabagna. Okay, welcome. So I'll stop the class here. Thank you.
Yes.